will start with the first session, and I'm presenting you the panel list who will be moderated by Mr. Martin Elegast. I will give him now the floor to present the overall day, and start then with the first presentation which will be conducted by Mr. Martin SCHLAURI, grain milling expert at Buhler. Mr. Martin Elegast, the floor is yours.
Thank you very much, Marine, and good morning, and thank you all for joining the Milling Forum today. I mean, those very special times. We had a very interesting day yesterday, all about cleaning and tempering the wheat, and now today it's time to mill the wheat. We have a very special program today, and a very interesting program. We're gonna have 4 sessions today. And we're going to start with a person who is very well known by most of you, Martin SCHLAURI. He is a milling technologist. He worked in different management positions at Buhler, and especially for Middle East and Africa. He actually developed 5 years ago the African Milling School, and I'm looking very forward to his presentation, which is all about the milling flow sheet design, the base of milling efficiency. We're going to hear a lot about flow yield and different qualities. Martin, the stage is yours.
Thank you. Fine. I'm honored to start the first session of the second day and to share with you insights about the flow sheet design. Now, if we start to think about the flow sheet, we need to know first the raw material, our wheat. Now look at the wheat kernel as it is shown on this picture. It is composed on with three different parts. We start with the endosperm. The endosperm represents 82.5% of the whole kernel. The bran, all in all, 5.5, 2.5, 7, 15% of the total kernel is bran. And when we go for the germ, we find it's 2.5%. Now, the amount is 1, but the ash is the other. So if you look at the ash content, you find the endosperm around 0.4, 0.5, so it's low. If you go on the bran, it's very interesting. The epidermis cross cells, the outer part is 2 to 2.5, but the highest content of ash means minerals, is the alloiron. So alloiron is key to separate from the flour to get a low ash flour. Now, if your boss will ask you, now Martin showed you a slide, it shows 82.5% of flour. Can we make 82.5% of extraction? Maybe not. No, for sure not, because this is the ideal case. If you have a fully developed kernel, it works. But we all know we have a mix of shriveled, we have a mix of broken, of shrunken kernels. So it brings us down to 78, 79% of extraction. So this is the base, and let's summarize. The center of the endosperm represents the flour with the lowest ash content. This is important while designing the flow sheet. The ash content increases from the center to outside, and the alloiron, what we just learned, has the highest amount of minerals of ash. Now, the biggest challenge is to separate alloiron from the endosperm. This is where we look in this picture in between here. The nature has not helped us. It would be easy to separate epidermis cross cells, but it's not like that. It is just here in between. So all this starts in the cleaning. We learned yesterday from Michael how important is conditioning. On the conditioning, we start the base, how to separate alloiron from the endosperm. Now, every miller has a dream, and I hope the dream becomes true, that you will be a member of a team designing a new mill. That's great. That is something we have a know-how, we can implement it. When starting a new project to design a new mill flow sheet, the first question is the target capacity. What will be the capacity of the mill? Second, we need to understand the raw material, the wheat where it is, the mineral content of the wheat, the test weight, but also the moisture from where it comes and on which moisture we need to mill it. The requirements of the finished products, how many flowers we need to produce, the target yield, the ash content, but also the moisture content of the flower, water absorption. It's a parameter we learned yesterday. It is important to know while designing the flow sheet. And do we want, yes or no, semolina extraction? Byproduct, also to know, is it a mixed bran or a coarse and a fine bran? Now, when we talk about flour, there is always the question, do we have a straight run flour or a divided flour? What is the difference between a straight run and a divided? The very typical of a straight run is the whole wheat. If you make whole wheat, it's straight run because it's from the whole kernel, 100%. The ash, what is the ash on a whole wheat? Equal to the wheat. So wheat coming in with 1.6, 1.7, also the whole wheat flour, if we don't take away any bran, will be 1.7. Divided, some call it split flour, will be a patent flour, a low ash, below 0.5 maybe, can be a brown flour, 0.75 ash, or a baker's flour, 0.6, 0.65 with a pollard, and that all can work in two. So you have two flour streams, a patent flour and a brown flour, or a patent flour and a baker's flour. When we talk about straight run, it can be a straight run baker's flour or a straight run home baking flour. So this is to be cleared before we start to design the flow sheet. Fine, now we are ready and we can think about the flow sheet. The flow sheet is the language of a miller. If I design a flow sheet, my friends in Egypt, in Kenya, in China, in America, they can read it. Without understanding German language, they can read the flow sheet of a mill. So we need to have specific terminations. So when we talk about the flow sheet, we talk about breaks. That is the first row. We talk about graders, divisor, dividers. We talk about bran finishers. We talk about purifiers. Then it comes to reduction. In the reduction, we divide it into clean semolina, composite semolina, collecting passages, and middling passages. This goes through the whole concept of designing a mill flow sheet. Now, this is the first, but now what is the landscape of a mill flow sheet? We start from top down and from left to right. And when we talk top down, we divide it into quality. We just learned inside the endosperm is the low ash endosperm, low ash flour. So that is called first quality. It comes off first break, second break. Second quality from third break is higher in ash. Third quality is even further high, and the fourth quality is usually the bran pollard going to a brown flour, going to high ash end products. So understanding this, we can design a flow sheet. That would look like this, very straightforward, a 4-roller mill flow sheet. We have first break, second break, third break. We can divide fourth break, coarse fine, fifth break, coarse fine. We have the dividers, the divisor or the graders, we have the purifiers and the reduction rolls. This is the classic, but we have nowadays in almost all the cases a hybrid solution. Means double roller mills. Coming to double roller mills, where do we apply the double high roller mill? And if understanding this concept, you will know how to apply it. Always where we have product of the same quality. For example, first break, second break, C1, C2, or it can be C5, C6. So this could be the solution to apply a double high roller mill. Double high roller mills have the advantages of cost efficiency and space savings. So this would be then a combination B1, B2, C1A, C2A, C5, C6, but could be also C8, C9, always product of the same quality. So summing up, quality separation in a milling flow sheet means stock of similar quality ash content has to join the same passage. And in smaller mills, you may need some compromises. Smaller mills can be below 100 tons. But in case there is a conflict, disregard granulation and look at quality. So looking at a flow sheet, we see and you find different flow sheets, flow sheet concepts. So we learned also the weight has an impact, how to design a flow sheet. This would be a typical hard weight flow sheet. And you will notice, or you are noticing, first of all, brakes. We have 1, 2, 3, 4 brakes. Wow. Why not 5? Hard wheat has a very thin bran. It's easy to separate the bran, but it's hard to grind the endosperm. So few breaks and a long reduction passages. So we go up to C10 or even further. On hard wheat, we have a huge amount, big amount of semolina, so it's recommended to have purifiers. Let's look at the extreme. Soft wheat mill. A soft wheat mill is hard to separate the bran, but it's easy to make the flour. So in this case, we have more breaks. We go up to 5 breaks. We may not need purifiers because on soft wheat, usually easy to make flour, hardly get any semolina out of it. And the reduction rolls can be shorter. It can be ending at C6, C7, C8. So it doesn't need a long reduction. Now, you will be a lucky miller if you have a soft wheat mill and a hard wheat mill. But very often these two comes together. And if they come together, it's a multi-grist mill. In a multi-grist mill, we need to consider the hard wheat as well as the soft wheat. So we have 5 breaks as we use for soft wheat. We have purifiers as we use for hard wheat. And we have an extended reduction rolls because we need to grind the hard wheat. So that is the concept, the principle. Now let's summarize: 4 breaks for hard wheat, 4.5 or 5 breaks for soft semi-hard wheat with extraction 76 to 80, which is more the general mill. Then the last 2 breaks, in order to have a good separation of the starch from the bran, we usually divide B4 and B5 into coarse and fine, and 2 times bran finishers. I will come back on that topic. Now, if you look at your flow sheet, you find some specific granulations. What is a granulation? A granulation is a particle size of your semolina and middlings. So every granulation has an upper and a lower limit of the particle size. And every mill has a specific number of granulation. If I will ask you, what is your mill flow sheet designed with a 3 or 4 or 5 granulation? You may wonder. You go back to the flow sheet and you will find it. So the number of granulation is depending on the size of the mill, the number of purifiers you have or you want to install, and the extraction of the mill. So talking about granulations, what millers count? If I say a 4 granulation flow sheet, these are the range of semolina and middlings below the break stock, 1120, and above the flour. So in this case, we have 1, 2, 3, 4 granulations, from the coarse semolina to the medium semolina to the fine semolina and the middlings. This is the concept. So from here, from the breaks, we need the purifiers. It goes to the specific purifier. Now, a mill can be designed on a 3 granulation, which is a basic mill, can be a 4 granulation or a 5 granulation. Now, a 3 granulation flow sheet is usually used if you have a straight run mill, making some good baker's flour, home baking, but no semolina extraction, no patent, no split flour. A 4 granulation, maybe it's the mostly used. You have also the possibility of split flour, extracting a patent flour and a brown or a baker's flour in parallel. Then the granulation of 5 is usually only used in high semolina extraction, for high semolina extraction. And of course, all the durum mills have a 5 granulation. This is good to know, because if you change some sieves in your flow, always remember, don't change the border of the granulation. Purifiers are key. When we look at the purifier, what is the starting point? It's the product going or coming to the purifier. What is important on the product coming in? 3 things. Always remember a clear granulation range. It must be a range, let's say from 1000 to 600 micron. From 600 micron to 430, it must be a clear cut. Secondly, free from flour. The sieving efficiency of the sifter must take off the flour. This is the topic what we learn from Cedric today. And third, a purifier needs a consistent flow. Then it goes into the 3-deck purifier, air going up. So the first product coming through is the clean semolina. That's the premium, that's the first quality. Second product, semolina with some bran particles. Usually you go to a reduction roll, like a C1B, a composite semolina reduction. Then we have the overs. So the bottom sieve over is darker than the truths, but lighter than the others. Now there is one, let's call it a bridge for every miller to understand, is his purifier well set if the bottom true is looking similar like the inlet. These 2 products should have a same appearance, then you can be satisfied with the setting of the purifier. Now, sieves are important on the purifier. You get a granulation from a sifter, like 1120 to 600 microns. Now, you may have wondered why then on the purifier you don't have 1120, you have 1180 or even 1250. So you have a bigger, let's say more opening sieve at the purifier than on the sifter. Why is that? Remember, a purifier works with 2 actions. One is sieving and one is the air flow. So air segregation, classification. So when we have a sieve, the air always passes against the stream of the semolina, of the product. So that means we need to get allowance between the semolina and the sieve opening. And these are these added 60 to 120 microns, so that the biggest sieve of the purifier should be 60 to 120 micron bigger than the top sieve of the granulation. How to arrange the sieves? It's a key. The biggest opening is always on the top end. So we are starting to give to the semolina always a chance for the next sieve, which is more open, more open, more open, either to go through or to go over. And the air will keep the bran or the light products floating. The same goes down. It will be the next, also the same structure. So we can say the sieves opening are smaller or are wider at the end or smaller at the beginning, and down we are getting finer. So we always have a next chance for the product to go through. Detachers. What millers can say, sorry to say this, it's a stupid machine, but it's an important machine. Without the detachers, you will lose extraction, and of course the flour quality will be different. So why do we use and why do we need to use detachers? We have smooth rolls on the reductions. They have a ratio between 1 to 1.25. So it's a combination between friction and pressure. And the high pressure gives you flakes. Flakes is semolina, is endosperm sticking together of the highest quality. So now what we need to do is to destroy, to damage this flake to be able to sieve out the flour. So this can be done by different type of detachers. Can be an intensive impact detacher, can be an impact detacher. When we talk about intensive, we talk about detachers which have 3, 4 rows or circles of pins, and they work very intensive. They are used in the clean semolina like C1A, C2A, C3A, but can be used also at the tail, at the end of the mill, just to make a higher extraction of brown flour. Or if you want to extract some section for atta flour, such an intensive impact detacher can give you a few extraction higher. Impact detachers are the basic, can be used for also composite semolina. Impact detachers can be used also with different RPM, so it can be a bit softer, middle, or more harder work. Impact detachers are always between the roller mills, like if it's a double roller mill after the second passage, so C1A, C2, you have an impact detacher and you go to the sifter. Or if it's a single roller mill, you have the roller mill, you have impact detacher, and you have the sifter. Bran finishers also, to gain the last percentage of flour out of bran, it's a must. Without bran finisher, we are losing endosperm in the bran. So we have 2 types. So I'm often asked, which one is for which application? There is a standard bran finisher. It's the solid machine with a rotor and the sieve. It is low maintenance, easy to operate, and very efficient. It can be applied for coarse and fine bran. For any standard mill, it works excellent. If you have a very specific demand on more brown flour, atta flour, anything like pollard, it can be the fiber type bran finisher. It's more aggressive than the standard bran finisher, and it has a very good efficiency in the fine bran flakes. Bran finishers should work twice on the bran. So always the second 2 breaks can be before fourth break and fifth break. If you have only 4 breaks, it can be third break and fourth break. So always after the last 2 breaks, you put a brand finisher. So like on this flow sheet, we have before coarse, before fine. We bring the product together to the sifter. We have an over, brand finisher 1. We have a second over, brand finisher 2. Brand finisher 1 coming from the sifter before has a sieve opening of 1.25. The brand finisher 2 is the finer stuff of 1. It goes to B5 coarse and B5 fine. Then we go B5 coarse, B5 fine. We also go to the sifter. The first is the coarse, second is the finer. Where we are going? To the coarse brand and to the fine brand. And if you wish, you can bring it together and you have a mixed brand. Brand finishers can be also used as pre-sifters. When do we apply this concept? If you have a bulky break stock, some semi-hard, soft wheat, the sifters are sometimes overloaded, or you need too much sieving surface just for the breaks. So there is a trick to apply the brand finisher as a pre-sifter before the break passage, or break sifter. So that means the brand finisher is taking off the coarse particles, the bulky particles, and it goes right to the next break. So from the B4 coarse, it goes after to the B5 coarse. And of course, from the B5 coarse, it goes to the brand coarse. It's finishing. So this is called a pre-sifter, and it's a good concept to release the product from the sifter. Now, how do we design a sifter, and what are the very few key elements on it? First of all the overs must be to the left. So if we have a sieve size of 500 micron and we want to take off the overs, they go out to the left. Overs are on the left. The truths are to the right. So if you read a flow sheet, and even from a copy which is not anymore so clear, you know overs to the left, truths to the right. Then the overs you don't put on the bottom line, you always put a bit higher up. So we know it's over, and the truths are on the line. Then we have numbers, 6 times 600. What does it mean? You have 6 sieves of 600 microns. Goes down, you have 5 sieves of 425 microns. We have an over, and we have a true. So this is the basic and the language of a mill flow sheet. So looking at the real case, we have a first break, 6 sieves of 1.12. Now what means that? Why now the millers write 1.12? It can be that above 1 millimeter, 1000 microns, you write it in millimeters. So 1.12 means 1120 microns. It's usually also the scalping sieves are wire mesh. So wire mesh very often are specified in millimeters. Whereas down 600 micron is definitely a PA sieve, 300 micron, 112 micron. Here we go to P1, purifier 1, we go to purifier 3. We have the divider, so from the break, and we have the flour. Here we have a second break. We have 2 types of sieves, 2 times 1800 micron, 6 times 1400 micron. Next is a 900 micron, 530, 300, and 100. I would ask you, if we would be in a dialogue, why a miller has chosen this concept. It's strange, but you may find in your flow sheet some very specific sieves applied in your sifter. You may know only if you know the history, like why this is are coming. It could be this mill was designed for a hard wheat, but then changed to semi-hard. So 1800 micron helps to faster separate the granulation below, and it doesn't mean that you mix the product, but you have a faster release of the semolina below, but after you go to 1400 because that's your target range. So this is just showing a mill. The mills today, the mills are food processing. Food processing means you need to have it clean. That is, I would say, the biggest mill under one roof in Africa. It's in Nigeria. Or these are sifters, which can be also nicely designed, clean, no dust around. Purifiers, we learned. So let's conclude. When we talk about the conclusion, we can say milling is a selective grinding process. It starts from the kernel and it ends with a clean flour and a clean bran. What means a clean bran? It's a low starch bran. The flow sheet design is based on the raw material and on the finished product. And of course, the flow sheet has the impact on the extraction. You can be the best miller. If your flow sheet is poorly designed, you don't get the best extraction. How to measure this is tomorrow, not today. We have Peter. He will talk about ash curve, which is an indication how your flow sheet and of course how you're setting the mill. And of course, the flour properties. With the flow sheet, you can get your best gluten and your best water absorption. Without having the proper flow sheet, you may not reach. Thank you. That's it.
So thank you, Martin. Very well done. And you explained us a very big and complicated topic in a very clear and logic way. Thank you very much. And I'm quite sure there will be a lot of questions coming up. So I ask the audience to type it in the chat. If you have any questions, please type it in. Meanwhile, I have a question for you, Martin. There are worldwide mills actually which operate without purifiers. The question here is, can they actually produce good baker's flour, or can you explain it a little bit more in detail, Martin?
Yes, that's a good question. And also in Europe, if you go to France, in the French mills usually have no purifiers, but they make a good flour. We all know the French baguette is one of the best bread. So a purifier is needed for a purpose. It can be needed, of course, if you want to extract semolina. But it is also needed if you want to make a split flour, like a low ash patent flour, together with a baker's flour. But if you know from the very first day that it is running for the 365 days on a home baking, on a straight run baker's flour, the purifier will not help a lot to give you higher extraction. This is also shown on an ash curve. An ash curve will end at 78, 77, 78 extraction at the same point. Having a purifier or no purifier will not have a difference. So the conclusion is, yes, if you want to extract semolina or you want to make split flour, purifiers are needed.
Okay, thank you very much.
الرينج بتاع العاش كم؟ الرينج بتاع العاش ايوه شفته.
Okay. There are still no questions in the chat, so I have another one for you, Martin. So once again, please type in your questions. Martin, if the flour extraction is low in a mill, what could be the reason for it?
If the flour extraction is low, there is always a number of reasons behind. First of all, it's definitely, let's call it the maintenance. Maintenance means the condition of the flutes, condition of the sifter. This is the number one. If we have worn out flutes, if we have sifters who are not efficiently sieving, the extraction will be low. Second is the setting of the rolls. Just in the next session, we will hear about brake release. So Stefan will give us his know-how about brake release. If the brake release is not set properly, if the brake is not set properly, the extraction will be low. So we have definitely parameters which we should follow in the whole concept from wheat to flour to assure that we have a good flour extraction. And also conditioning of wheat when we have a low tempering time where the alloiron is sticking on the endosperm, it will be hard to separate alloiron with the bran, and we have, as a consequence, also low extraction with an ash, given ash. So let's say it's the flow sheet, it's the conditioning, let's say it's condition, it's the maintenance of the machines, and it's the operator's setting.
Okay, thank you very much, Martin. We have some questions coming in now from the audience. The first question from Dory about, we see some mills, the question is, we see some mills that using fluting rolls on reduction system, and some are using smooth rolls. Why do they have fluting in reduction?
Fluting in reduction can have two reasons. In the early days, there was the idea to take some more semolina, especially in some regions where semolina is a big market. Then the C1 product can be also brought back to a purifier, or some middlings can be extracted. Then I would say it's in the older days, the starch damage, let's say the water absorption was not so key like today. If we have fluted rolls on the first and the head reductions, we will not get the same starch damage, and consequently the water absorption will be lower. So mills need to decide on which way to go. It can be changed, and many millers have changed from fluted rolls to smooth rolls. If your fluted rolls are fine, in good condition, you can make a good flour with a good gluten, but lower starch damage.
Okay, perfect. Thank you very much. Another question would be from Esa from Algorea. What is moisture in wheat germ?
Moisture in wheat germ. The wheat is conditioned, and the bran, the germ, takes the water. If conditioning starts with the tempering time, the water penetrates. So if we go through a milling process, the bran, like the germ, are losing moisture. So also yesterday was a question, what is the moisture of the bran? My experience is it is even lower than the flour. And the same on the germ. If we go through the milling process and we have a germ extraction, the germs should be around 13, 13.5, let's say, below the flour. But not much below, because it holds the water easily, it is absorbing the water, and it's usually around the 13 to 14%.
Okay, thank you very much. Another question is from Boniface Izunuyoya. I hope I pronounced the name right. He says, thank you, Martin. You said a lot on extraction. From your experience, when you have a blend of hard and semi-hard wheat, you can mill separately and blend the flour or blend the wheat during tempering. In which of these ways can you maximize your flour extraction?
So it all starts with, let's call it the protein content, hard, semi-hard. When you talk about the semi-hard, it can be 11.5, 12, 12.5, a hard can be 13 and higher. If the difference is too much on the protein, means also the hardness, we should condition it separately, and then you can still blend it before first break. But the conditioning time, as we learned also yesterday, is different from a hard to semi-hard. So there are actually two options to condition it, to clean it, condition it separately, and blend it before first break. So both are mellow, both are mature, and then you go to the milling. Or you go to the extreme and you separate hard and semi-hard, you grind it and you blend the flour. So my experience taught me that I would say most of the cases separate the grain in cleaning is an advantage, and blending it before first break is simplifying the process. So I would do that without blending the flour afterwards. Blending flour needs a facility, needs installation. If you have that, you can do that, but it should only be applied in the extremer flour properties, like a very high protein or a different ash content.
Thank you very much. We have another question regarding roll fluting from Ihab Ghanim. And he asked, what is the relationship of the flow sheet and design of roller like sharp to sharp and dull or dull to dull?
There is more a relation between the design of the flutes and the wheat to be ground. So let's say if we start on a hard wheat, we go on a dull, more dull flutes. So first break, second break definitely will be dull. Then third break can be also on a hard wheat dull, on a softer or semi-hard wheat, it will be sharp. Millers usually decide on dull, sharp. The mix of dull, sharp, dull, it's given to durum millers, but not on a soft or semi-hard or hard wheat mill. Now, this is more, as mentioned, the hardness of the wheat. The mill, of course, needs to take then the semolina. If we have sharp, the semolina amount will be higher, and the starch, let's say the bran particles will be higher. So it needs more purifiers to purify if you have sharp on the breaks. So conclusion is first break, second break, it's dull. Third break can be either or, and the fourth and fifth break usually are sharp.
Thank you very much. We have a very interesting question from Andy coming in, and he asked, when everything is kept constant in the flow into the mill, why do sometimes see a sudden drop, for example, 2% in water uptake in the flour for a short period? No change to wheat intake condition times, etc.
Oh, it's very specific, and we would need to look at it. There is consistency of wheat is important. Very often it happens that millers think that the wheat is consistent, but it can be the bottom of a bean. It can be, of course, the raw wheat bean, can be the tempering bean, and always there is a segregation. It can be the best designed bean, there is a segregation, so the bottom of the bean can be different wheat. Usually it's a bit lighter. The heavy wheat passes fast. So it must come either from the wheat, which is not consistent. Then, of course, at the end, you have also a different water absorption, because protein is key in water absorption beside the starch damage. The other thing is, of course, if there is a parameter in the mill which is changing, can be whatever roll setting, but this is definitely the operation. I can only see there must be something different from the, let's say, from the starting point, which is the grist.
Okay, thank you very much. Another question, a little bit longer question from Khalid Al-Haza. Thank you, Martin, for the useful presentation. My question is, sometimes we get asked to produce flour that has different specification than what we normally produce. For example, a customer asks for softer flour, so we have to change the sieves. this cause a temporarily downtime for the mill and waste in time and capacity. How can we overcome this problem? Is there any developed technology that can help us with this problem?
Yeah, let's say it's one thing is in the operation. Sometimes a different flour with a very specific property can be extracted as a split flour. So if I know I need a softer, I need a lower protein and higher protein or different ash, I could do it in a second flour stream. Not easy always or not possible always, but if it's feasible, that may be a case. If not, it is definitely an issue that changing sieves need a downtime of the mill. So we need to stop the mill, we open the plant sifter and you get it ready for the next. So either the flow sheet can be designed with flap boxes that you can change the flour sieves by different streams, adding through a flap box, or it needs a downtime to change the sieves.
Okay, thank you very much. Another question regarding roller stands from Hassan Momo. He asked, you said in your lecture that double high roller mills are used for same quality products. When space is available, which is preferable, single or double high rolls?
Single or double is now explored since about more than 20 years, and there is a very profound know-how behind. So the rule is, if you produce basic flour and two flours, you can easy and usually use double high. If the extraction of flour is very different and you have a higher number of end products, less double roller mill will be an advantage. So it's all about the finished product. We can say, and millers confirmed, that the extraction can be the same, the starch damage can be the same, ash is the same. All about how many type of flours you want to produce. So again, if you want to have split flour 2 or even 3, then more flour streams will be an advantage.
Okay, thank you very much. Another question from Olatunji Lawal, which is not really a question, but maybe you understand it. A typical shelf life for a flour is 3 months. And we also know flour matures with age. It's not really a question, but maybe you can explain a little bit about shelf life and also the aging of flour.
3 months is not so typical. It all depends about the climate and the moisture. Some countries, I know in Africa, they have even by the government reduced the moisture to 13%, and shelf life is even double, it's 6 months. So shelf life depends on the environment and depends on the moisture of the flour. But the other point is aging. Aging is important. What happens during aging is the maturation of the gluten, the natural oxidation of the gluten. Now that happens in the first, I would say 6 to 8 days in warmer climates. In cooler climates can be even 2 weeks. So aging means it's the oxidation and the gluten becomes more elastic, and it's definitely an improvement in the baking. So aging and shelf life usually is very different. Now, aging is only important for baker's flour. The bakers, they buy the flour and usually they don't keep it for 3 months. They bake it maybe the next day. So now there it is important to keep the 6 days, 8 days from production until baking, until processing should be 6 to 8 days. That is definitely a more stable flour, more consistent end product.
Okay, thank you very much. Regarding ash curve, we will have a presentation in later on from Peter Lloyd. But there's a question to you, Martin, regarding the ash curve from Solo Tikaya. The question is, does the flow sheet design affect the method used to generate the ash curve?
Yes, the flow sheet design gives you the slope, or let's call it how flat the angle of the ash curve. So if we go strictly through the quality grading, so not only by size, but the quality, which we learned just at the beginning of my presentation, you have a flat ash curve, and then it starts to go up. So definitely, every mill has a different ash curve. And that's why an ash curve should be pulled out after commissioning. It should be hanged up in your control room so you know exactly how is the character of your mill, and that is given by the flow sheet. And when you have it done, you may repeat it, but not every week, not every month, maybe once a year. But at least you know the character of your mill, and you know how much of patent flour, how much of baker's flour you can extract.
Perfect, thank you very much. Another question coming in from Serendip Flour Mills in Sri Lanka. Any idea how much percentage of starch damage can manage with roller setting, and could please advise how to get the advantage of detaches to control over this?
Yeah, okay. The starch damage, if we talk about starch damage, we always do it because of water absorption. So we want 62, 63, even maybe 64 in extreme case of water absorption in the flour for bakers. Now, high water absorption always depends on the two, on the starch damage and on the gluten. How much gluten? We all know gluten can absorb 3 times, so let's say 200% of its weight. So if you have a low protein, low gluten flour, water absorption is not really feasible. Then you start to damage the starch. We learned yesterday is damaged starch can absorb 3-4 times of its weight. So this can be done with roller mills. Now, the wheat conditioning is key for damaged starch and the rolls. Now, we always start on the wheat. When we want to have a damaged starch, the British are experts on that. They keep conditioning time low to keep the core of the endosperm still vitreous, and they reach a higher damaged starch. But that is not always possible because you will lose some moisture. But on the other side, the rolls, C1, C2 make starch damage. All the rest is only cosmetic. So we need to work well on the first 2 reduction rolls. They need to be well tapered, having a good surface, not too smooth, not too shiny, and you will reach an excellent starch damage.
Thank you very much. Another question from Salim Makul. Assuming that we have granulation for flow sheet and we grind semi-hard and soft wheat, in that case, do we get low ash value from the purifiers?
Yes, we can say, but on the soft wheat and purifiers, they don't like each other. The soft wheat, first of all, you don't get a bigger amount on semolina. And secondly, the purifiers always build up some flour attached. So it's not always easy, a real proper soft wheat to pass through purifiers. I repeat again, the British millers, they have these 2 extremes. What they did, they bypassed the purifiers. On the very proper soft wheat, they say for what we need purifiers, it's only disturbing. So they go bypassing on soft wheat, bypassing purifiers, but depends on soft. Soft is always depends on below 10% protein, 9%, 8%, that is the real soft. But very often the soft is not so soft. You can use purifiers, and then, yes, you have an advantage too.
Okay, thank you, Martin. Another question which goes also in the same direction and overlapping a little bit from Ali Tavanai. The question is, what's the standard or ideal number of purifiers, mid reduction, low grade and tailing passages for a semi-hard mill to avoid mill adjustment complexity and optimized investment cost, in your opinion?
Good. Now here we come back into the granulation. The mill, if you have a semi-hard, will have usually a 4 granulation. So that starts on 1000, 1120, goes down to 600, and we have coarse semolina, middle, fine semolina, and middlings. Now, usually we say, at least if you want to go for an advanced flow sheet, you should maybe 3 purifier granulation. So that will be the coarse semolina, the middle, and the fine semolina. Middlings does not help, and middlings is also creating an issue if you change wheat grist, because on a semi-hard or softer wheat you have much more middlings than on a hard wheat, and if you would use a purifier for those, you have a big issue and a real challenge on balancing the mill. So let's say 3 granulations should be purified, and you have a very consistent flow.
Thank you very much. And now another question from India, Jaya Krishna flour mills, which goes in energy consumption. And the question is, what should be a target power unit per ton of wheat from intake to flour handling with automation?
So we talk about power consumption. Now it's a case to case. So let's say from wheat intake, wheat storage is very, very specific. Every miller has his own size and number and turnover. I can only talk about cleaning and milling because this is more standardized. So now I give a number. Maybe I'm not that specific, but we can say 0.8 to 1 kilowatt hour on cleaning. Then we have maybe 3.5, 3.8, 4 kilowatt on milling. So around 5.2 altogether from the wheat to the flour.
And it depends very much on the flow sheet design and the design of the complete mill, right?
Correct. And this is now, again, why millers always are in a challenge where we should go. We like to have complex flow sheets, but complex flow sheets give also higher, how can I say, consume higher power because we have more lifts, we have more machines. Just a purifier consumes a lot of energy running 24/7 just for the air. And this is where we can have differences between the mills.
Okay, thank you very much. We have 2 questions left. I think we can make it in time. There's another question from Ihab Ghanim. He's actually, he has a question to his question before. And he says, I asked about relationship between flow sheet and roller design, but I want to know about the relation between the sieves number and roller design.
When we talk about sieve number, is it the sieve opening or the total number? Usually, if we talk about sieve number, when we talk sieve opening, it's all about the end product. We know we have different demands. So the rule is if you have a good baker's flour, it should be finer than a home baking. So a baker's flour is below 150 microns. A home baking, which is just used for pastry, can be 180 microns. You have pasta flour, 212 microns. So this depends on the task and application of the flour.
Okay, thank you. Another question from Sunday OD. What is the major determinants of purifier sieve arrangements?
The major key is the upper, let's say the coarsest sieve. This is what I explained. We need to look at the granulation of the product coming in plus 60 to 120 microns. So we need to give allowance to the product to pass. If we don't do that, we have too much of the good semolina flowing to the next break. This is a loss in extraction. So we need to have the purifier sieves more open than the sifter, the plant sifter sieves. And then it's just the biggest sieve is at the top end, and then we gradually close and we gradually close down. But these are the two. First of all, design, or let's say calculate first the biggest sieve on the purifier and go in steps down.
Okay, thank you very much, Martin. Another question from Salim Makul is coming in, and I would propose that would be the last question. And the question is, what is the maximum percentage that I can take finished product semolina from purifier directly without impacting the quality of straight run flour for bakery applications?
This is similar to patent flour. If you have a split flour, some like to extract some patent flour, low ash, and at the same time make a baker's flour. It's also what comes in. So if you have a strong wheat, higher protein wheat, you can go on 10, 15, 20%. If that wheat is already, the blend is weak at the beginning, you may only extract 4 to 5%. So it is giving, let's say you take away the best part of the kernel, which is the center of the endosperm, either by the semolina or if you have a patent flour. So it's always impairing the remaining flour. So it's a case to case. You really need to look at the raw material, let's say not raw material, the grist coming to the first break. What does it allow? How much you can take off to maintain still the properties, the parameters of the baker's flour. And that can be very, very different from mill to mill.
Okay, Martin, I just got the message from Miriam that we actually missed 2 questions. I think we still have a little bit time. So Miriam, can you please read those questions I have missed, please?
Yes, sure. So let me go back to the chat. So we had one question from a participant called admin. Can we produce semolina with non-extraction effect?
It is, let's say, it's same like the last question, that if we extract semolina, you have an effect on the flour. Semolina is, let's call it a semi-product of flour. So at the end, you always have to count both semolina and flour make together. So it has an impact, you cannot avoid it.
Okay, thank you. And the next question from Ola Tunjilawal. A typical shelf life for a flour is 3 months, and there is also a myth that flour matures with age. We have, however, observed that quality indices and baking performance of flour drops from about 6 weeks. Could this observation be linked to milling or inherent qualities of wheat?
I would say less to milling, but more to the enzymatic activity. So when we talk about maturation, it's the first 6 to 8, 10 days in warm climates, always thinking about Middle East Africa. And that means the property improves. So get the gluten more elastic, stronger. It stays for some time, but enzymes are not sleeping. If you have a humid, warm environment, that both effect to activate enzymes. And when we talk enzymes, there can be the amylases, but also the proteases. So it can start to degrade the flour if it's too long. So I would say that ideal can be the 2 weeks, 3 weeks, 4 weeks. And if it's over 6 weeks, yes, I noticed too, flour may lose some properties, some good characteristics.
Okay, thank you very much, Martin, for the answers of the questions.